over, find the cable in the dark, and just plug your phone in right before you fall asleep.
Right. Totally thoughtless. We don't even look at the outlet anymore.
Exactly. We all do it. But I mean, imagine plugging in a device that pulls like the equivalent electrical power of a small neighborhood.
Yeah, that's a whole different scale.
And now visualize millions of other people doing that exact same thing at the exact same minute every single night.
Right.
That invisible collective strain that is the actual front line of the electric vehicle revolution. And today, we are taking a deep dive into data from the International Energy Agency's 2025 Global EV Outlook.
Which is a massive report, by the way.
Oh, huge. And we're cross-referencing it with a highly critical counter-report published by OPEC, and then grounding all of that macro global math with this really granular academic study of residential power grids in Houston, Texas.
You really cannot divorce the big geopolitical shift from the physical reality right on your street.
Right. The goal today is simple. Figure out if the wires running outside your bedroom window are about to just melt down under the weight of global economics. Okay, let's unpack this.
Yeah, let's do it. Because to grasp why the grid is under threat, we first have to look at the unprecedented scale of EV adoption that's just sweeping the market right now.
Let's start with the sheer volume, because the International Energy Agency, the IEA, they put out numbers that, honestly, they look like typos at first glance.
They really do.
In just the first quarter of 2025, global EV sales jumped by 35% compared to the previous year. 35%.
Wild.
And their projection is that by 2030, electric vehicles will make up 40% of all global car sales.
Right?
40% of all new cars on the planet in just 5 years.
It is a staggering acceleration.
Yeah.
And to understand the mechanism driving that speed, you only really need to look at one catalyst, and that's price parity.
Right. Because for a long time, EVs carried this heavy premium. You know, they were luxury items or like environmental statements.
Exactly. But the IEA report highlights that in China right now, 2/3 of battery electric cars are actually cheaper than their conventional gas-powered equivalents.
I want to focus on that for a second, because we aren't talking about government subsidies bringing the price down to match gas cars, right? We are talking about the upfront sticker price actually undercutting the internal combustion engine.
Yeah, the economies of scale happening in Chinese manufacturing have they've completely inverted the traditional automotive pricing model.
Wow.
By concentrating their supply chains and just achieving this unparalleled volume, they have driven the per unit cost of an EV right into the floor.
It totally reminds me of the smartphone transition, like a decade ago.
Oh, that's a great comparison.
Yeah, because there was this window where a smartphone was an expensive business tool, right, for early adopters. But the moment the smartphone became cheaper to manufacture and buy than a basic flip phone, the floodgates just opened. It became the default almost overnight.
And just like the smartphone revolution, that price inversion, it does not respect international borders.
Right.
Chinese manufacturers are aggressively expanding their overseas operations, mainly to avoid domestic saturation. So they are heavily targeting emerging economies rather than just trying to compete in the traditional Western markets.
Yeah, the data points to places like Thailand, Brazil, Indonesia, Mexico. Chinese exports to these regions are just flooding the market.
Right.
Like in Thailand, battery electric cars have already hit price parity almost entirely due to Chinese imports.
Which is a huge shift.
It is.
Yeah.
And the implication for you, the listener, is that the EV transition is no longer this localized trend for wealthy enclaves in California or Norway. It is an active, snowballing global reality that fundamentally rewrites global trade.
Which logically leads to an assumption about oil, right? If EV sales are booming globally at this breakneck pace, the general public naturally assumes global oil displacement. You know, the amount of crude oil we no longer need to pump from the ground must be accelerating at that identical pace.
I have to admit, that was my exact assumption. More EVs equals less gasoline burned. It just seems like rudimentary math.
Yeah, it makes sense on the surface.
But here is where the data gets incredibly complicated. And it actually sparks this fierce debate between two heavyweights, the IEA and OPEC. OPEC published a direct critique of the IEA's outlook.
They did.
And when you put both documents side by side, impartially, the implications for global energy markets are enormous.
What's fascinating here is that both organizations agree the landscape is shifting, but OPEC pointed out a critical, somewhat buried revision in the IEA's own numbers.
Right, the revision.
Yeah.
Hmm?
Last year, the IEA projected that by 2030, EVs would displace about 6 million barrels of oil every single day.
Okay.
But in this new 2025 report, the IEA revised that number downward to just over 5 million barrels a day.
Wait, I have to stop you there because the math feels off. The IEA still projects roughly 250 million EVs on the road globally by 2030, right?
Right.
So if the total number of cars hasn't changed, why on earth would they drop their oil displacement projection by almost 1 million barrels a day? I mean, a car is a car.
Well, a car is definitely not just a car when it comes to oil consumption.
Okay, fair point.
The total number of projected vehicles held steady, sure, but the geographical map of where those vehicles are being driven shifted drastically. In this new outlook, the IEA slashed its 2030 EV sales penetration forecast for the United States. They dropped it from an expected 55% market share down to just 20%.
Dropping from 55 to 20% is a seismic revision.
It really is.
And the IEA report attributes that drop specifically to expected rollbacks in U.S. federal subsidies and loosening fuel economy standards.
Right, and you combine that with a stagnation in European sales as their own supportive schemes expire, and the Global Growth Center tips overwhelmingly toward China.
Wow.
Yeah, by 2030, China is projected to hold roughly 60% of the entire global EV market share. That is about 150 million vehicles. And this geographic concentration, that's what solves the oil displacement mystery.
Okay, wait. How does moving a sale from the U.S. to China change the actual amount of oil saved?
It comes down to consumer preferences and the physical size of the vehicles. The American automotive market is dominated by heavy, long-range vehicles.
Like trucks and SUVs.
Exactly. An electric Ford F-150, or a massive SUV, displaces a significant amount of gasoline. The Chinese domestic market, however, favors significantly smaller, lighter vehicles.
Okay.
Furthermore, their market features a much higher proportion of plug-in hybrids compared to fully battery electric vehicles.
Oh, I see. And a plug-in hybrid still has a combustion engine, so it still burns some gasoline.
Precisely. So a fleet of 150 million smaller cars and hybrids in China simply displaces far less total crude oil per vehicle than a hypothetical fleet containing millions of heavy American trucks and SUVs.
That makes perfect sense of the math. But, why should you, the listener, care about a 1 million barrel a day revision in some geopolitical forecast?
Sounds pretty abstract.
It does. But because this debate between OPEC and the IEA dictates the future price of the gasoline you put in your second car, it dictates how your tax dollars are allocated for national infrastructure.
Exactly.
I mean, if the U.S. transition slows down while global oil demand remains stickier than expected, the entire economic calculus of the next decade changes.
And OPEC actually uses this shifting geographic map to point out an even larger hurdle on the horizon. They estimate that global electricity demand could jump by 780 terawatt hours by 2030 purely to support this transition.
780 terawatt hours. I don't even know how to visualize that.
Yeah, it's massive.
That sounds like a made-up sci-fi measurement for powering the Death Star, It is an abstract, almost meaningless number to the human brain.
It really is hard to wrap your head around.
Right. So to understand the physical reality of that demand, we have to zoom all the way down from these macro global oil markets to a single microscopic level, right?
Yeah.
A neighborhood in Houston, Texas.
Which brings us to the academic paper from the University of Houston and Centerpoint Energy, which is honestly an absolutely brilliant piece of statistical detective work.
It really is. To set the stage, utilities face this severe operational blind spot. Because of privacy laws, utility companies do not get an itemized receipt of your home's energy use.
No, they don't.
They don't know exactly which houses have an EV charger installed. They just see the total household energy draw. So if a neighborhood transformer blows out, the utility might not know it was because 5 neighbors all plugged in their cars at the exact same time.
Right. So researchers in Houston needed a way to see the invisible. They applied data-driven methods to aggregate neighborhood power data. Specifically, they utilized least squares estimation and kernel density estimation.
Okay, please explain those terms without making my eyes glaze over with calculus.
Sure. Think of it like listening to a full symphony orchestra and trying to isolate just the sound of the cellos.
Okay, I'm with you.
The researchers looked at the baseline electricity use of a neighborhood. The hum of the refrigerators, the air conditioners, the televisions. By creating a mathematical model of that non-EV baseline, they could subtract it from the total neighborhood power draw.
Oh,
Yeah. Once you strip away the background noise, the distinct, heavy signature of EV charging suddenly reveals itself in stark contrast.
Now, what they found in that isolated data is the absolute core of the grid challenge. First, they identified the equipment. They discovered that the average level 2 home charger in this area pulls about 10.5 kilowatts of power.
Which is a lot.
It is. For context, these level 2 chargers aren't the standard 3-prong plugs you use for your toaster. They are heavy-duty, 240-volt dedicated circuits. It's exactly like the ones you would use for an industrial clothes dryer.
Exactly.
But the crucial discovery wasn't just the amount of power, it was the timing. The researchers mapped out a distinct U-shaped daily charging profile.
And that U-shape dictates the entire future of electrical engineering.
Right.
If we break down the timeline of that U-shape, you can actually see the physical strain building hour by hour.
Walk us through a day in the life of this neighborhood grid.
Sure. So during the day, from roughly 8:00 p.m., there is a deep lull. The EV charging demand drops to a nadir of about 1.2 kilowatts.
Because everyone's at work.
Right. The cars are parked at office buildings or they're just sitting fully charged in driveways. But right around 6:00 p.m., the ramp-up begins. People return home from work, they plug in their vehicles, and the demand curve shoots nearly straight up.
And it doesn't just spike and then immediately drop off once the car tops up, right?
No, it plateaus. The demand stays incredibly high, pulling that 10.5 to 11 kilowatts of power continuously through the nocturnal hours, late into the evening and overnight.
Wow.
It isn't until about 4 a.m. or 5:00 a.m. that the charging finishes across the neighborhood and the U-shape drops back down.
To put that 11 kilowatts into perspective for a second, it is the equivalent of every EV owner on your block coming home from work, turning on 3 electric ovens on high at the exact same time, and leaving them running with the doors open until 3:00 a.m.
That's a great analogy.
Every single night. How does the grid physically break under that kind of load? Well, think of a neighborhood transformer like a muscle.
Okay.
During the day, it flexes when you run your air conditioning. But historically, power demand drops off at night. The transformer gets a chance to rest and physically cool down.
Makes sense.
But the introduction of this U-shape means that muscle is doing heavy lifting all night long. The metal components never get the opportunity to cool. Over time, the internal insulation degrades from the relentless heat, and eventually, it just overheats and snaps.
Which is terrifying. And the researchers noted this really interesting behavioral detail, too. Most of these charging events involve less than 50 kilowatt hours of energy, peaking around 20.
Right.
So the owners aren't even doing full 0 to 100% battery charges. They're just topping up their daily commute usage. But the sheer synchronization of everyone topping up at the exact same time creates that plateau.
Exactly. So how do local grids survive this?
Well, this is why the Houston study, which it was actually validated against similar U-shaped data from residential grids in the UK and Norway, it's a lifesaver for utility companies. By mathematically proving the existence and the timing of this U-shape, researchers basically gave utilities a predictive tool.
Meaning they no longer need to violate privacy laws to know exactly who has a charger. They just need the mathematical probability of a zip code's behavior.
Yes, exactly. Utilities can now monitor the broader EV adoption rates in a given area. If they know the statistical shape of the U, they can model the strain proactively.
That's huge.
They can identify vulnerable neighborhood line fuses and schedule replacements for high-capacity transformers before they melt down during a 9:00 p.m. charging surge. It completely moves grid management from a reactive scramble to proactive engineering.
But, fixing the local grid is only half the battle. Because for you, the listener, to confidently transition to an EV as your primary vehicle, you don't just need the assurance that your garage won't blow a fuse at 2:00 a.m.
No, of course not.
You need the assurance that you can drive the car across the country to visit your family. And if we solve the neighborhood grid, we instantly hit a geographical wall: public infrastructure.
Which is the ultimate bottleneck of this entire transition. OPEC's report presents a pretty sobering metric on this front. They estimate that global public charging capacity needs to grow almost 9-fold by 2030 to support the projected EV boom.
Wait, 9 times the current infrastructure?
Yeah. We need 9 times the current infrastructure built in just 5 years.
That is a monumental, almost prohibitive-sounding task. But the IEA data provides a strong counterweight of optimism here, showing remarkable progress already happening on the ground, particularly in Europe.
Right.
Currently, over half of Europe's entire highway network is covered by an ultra-fast charging station at least every 50 kilometers.
And a station every 50 kilometers practically eliminates the psychological barrier of range anxiety on major European routes. But it isn't just the physical availability of the plugs. The chemistry inside the batteries is evolving rapidly. The IEA highlighted new Chinese battery technology capable of adding 500 kilometers of range in just 5 minutes of charging.
I mean, 5 minutes for 500 kilometers fundamentally alters the psychology of the road trip.
Completely.
You are no longer mapping out hour-long detours at obscure strip malls to charge your car. 5 minutes is the exact same duration as pumping a tank of gas and buying a coffee.
It is. And this technological leap is also quietly revolutionizing sectors we previously thought were immune to electrification.
Like what?
Take heavy-duty trucking. Moving cargo requires immense power, and batteries are incredibly heavy, which, cuts into cargo weight. Yet the IEA reports that electric truck sales saw an almost 80% jump in 2024.
I found that statistic fascinating because electric trucks are still 2 to 3 times more expensive to purchase upfront than a standard diesel semi-truck.
Yeah, they're not cheap.
So why would fleet managers authorize an 80% jump in purchasing when the sticker price is that high?
Because commercial fleet operators do not evaluate a vehicle based on the sticker price. They calculate the total cost of ownership, or
Right.
TCO.
Right.
Over the lifespan of a heavy-duty truck, the cost of diesel fuel and the constant mechanical maintenance of a combustion engine far outweigh the initial purchase price.
Yeah.
Electric trucks have vastly fewer moving parts. There's no transmission to rebuild, no oil to change, and commercial electricity rates are highly predictable.
Oh, that makes sense.
The math has finally crossed the threshold where, over a 10-year lifespan, the electric truck is significantly cheaper to operate. Pure, ruthless economics are driving that 80% jump.
But we have to balance that optimism with the lingering physical reality on the ground. Despite the rapid growth in ultra-fast chargers and battery tech, traditional petrol stations still vastly outnumber public charging stations globally.
Oh, by a long shot.
The infrastructure build-out is locked in a desperate race against the manufacturing volume of the vehicles themselves. If car sales continually outpace the grid capacity and the physical chargers, the whole system bottlenecks.
It is a precarious balancing act. You have the aggressive manufacturing scale of China pushing adoption forward, colliding with the complex realities of infrastructure and policy slowdowns in Western markets.
Let's pull all these threads together. The transition away from the combustion engine is not a simple linear progression.
Not at all.
On one hand, you have a world where plummeting battery prices and aggressive export strategies in Asia are completely reshaping global trade and lowering the barrier to entry. On the other hand, you have shifting policy landscapes in the U.S., changing the fundamental math on global oil displacement, leaving energy markets trying to predict a moving target.
And underneath all of those macroeconomic forces, you have local utility companies relying on advanced statistical math to track invisible U-shaped stress tests on the aging power lines running to our neighborhoods.
Right.
The success of the global transition ultimately relies on the local transformer not overheating.
Exactly. So the next time you walk your dog in the evening and you see an EV silently charging in a neighbor's driveway, you aren't just looking at a car. You are looking at an intersection of immense global supply chains, contentious geopolitical forecasting, and highly complex local grid engineering, all vibrating silently inside that one cable.
It is the invisible weight of the future, plugging in every single night.
I want to leave you with a final, slightly provocative thought to mull over, something we haven't even touched on yet today.
Oh, let's hear it.
If millions of EVs are sitting in garages all evening, creating this colossal U-shaped strain on the grid, what happens when we figure out how to reverse the flow?
The concept of vehicle-to-grid, or V2G.
Yes. Imagine a future where the grid doesn't just feed power to the cars. What if, during those peak evening hours when everyone in the neighborhood is cooking dinner and blasting their air conditioning, the grid actually pulls power from those giant batteries sitting idle in the garage?
It's a game changer.
The utility company pays you for your car's stored energy to stabilize the neighborhood, and then simply recharges your car in the dead of night when demand is practically zero. The very thing causing the strain becomes the distributed battery that saves the grid.
It turns a liability into the ultimate grid asset.
Something to think about the next time you plug in your phone. Thanks for taking this deep dive with us. We will catch you on the next one.